let's look at rotational kinematics. We have discussed rotation in a previous lecture, so let's see what we did back then and how this lecture is going to be new. So remember that when we discussed uniform circular motion, we had a constant magnitude of the velocity. So these arrows here, which signify the tangential velocity of the object, had the same magnitude. The direction was changing as a result of the direction changing, we also acquired a centripetal acceleration, which was always directed towards the center of the circular path, and it had a constant magnitude of A is v squared over r, where r is the radius of the circular path. So we had a constant magnitude, changing direction, which meant that the velocity was changing, which gave rise to a centripetal acceleration that had a constant magnitude but different direction that always pointed towards the center of the circle. So that's what we had before. Now, what is changed is the fact that the magnitude of the velocity is no longer constant. You'll see that this arrow is a little bit smaller than the next one, and so the velocity is increasing. And as the velocity is increasing, even in magnitude, the centripetal acceleration is increasing as well. So the centripetal acceleration is still equal to v squared over r. So smaller centripetal acceleration corresponds to a smaller velocity, and the larger centripetal acceleration corresponds to a larger velocity. The centripetal acceleration still has a radial direction, so we will refer to it more as a radial acceleration at that point. And that is to differentiate the fact that in order for the velocity to increase, there has to be a tangential acceleration that acts in such a way as to change the magnitude of the tangential velocity. So now with this type of rotational kinematics, non-uniform anymore, we have a radial acceleration in addition to the tangential acceleration. The radial acceleration changes in magnitude because the velocity changes. The tangential acceleration is constant in magnitude. The direction changes, it's always tangential to the circular path. So this is what we're starting out with. This is the scenario where the tangential velocity is changing, meaning that there is a tangential acceleration, and the centripetal or the radial acceleration is also changing. So let's start defining some of the terms that we're going to be using. Now we have, instead of displacement, we're going to be dealing with angular displacement. So in this image, we have an object that is rotating around this circle. So when its position is here, we'll say that the angular position is theta naught, and then at a later time, its angular position is going to be some final theta, and this will be the angular displacement. It is literally an angle. So the relationship then between the arc length that this object underwent here will be theta times the radius of the path. So the arc length is r times theta, but we have to make sure that we measure theta in radians. And just a quick reminder, 2 pi radians correspond to 360 degrees. Then the angular velocity has the symbol omega, and the average angular velocity will be the change in displacement divided by time, so delta theta over delta t, and that's measured in the units for theta, which are the radians, divided by the units of time, which are the seconds, so it's radians per second. And then we can also talk about the instantaneous angular velocity, where we set delta t, we look at the limit in which delta t approaches 0, and that becomes a derivative. So we have the instantaneous velocity omega is d theta dt. Then the next concept, just like in linear kinematics, is acceleration, but this time it's angular acceleration with a symbol alpha, and the average angular acceleration is delta omega delta t, and that's going to be measured in the units of angular velocity divided by the units of time, so that's going to be radians per second squared. And just like with angular velocity, we can talk about instantaneous angular acceleration, and that is the derivative of the angular velocity with respect to time. So the kinematic equations for rotation are very similar to the linear kinematic equations, where we basically substitute the letters. So here we have angular velocity final is angular velocity initial plus angular acceleration times time. Before we had just v equals v naught plus at. Now we have final angular displacement is initial angular displacement plus initial angular velocity times time plus 1/2 angular acceleration times time squared, just like before. And the final equation is final velocity squared is initial velocity squared plus 2 times acceleration times displacement. And notice that this time I didn't even say angular, because it is true both for linear terms and angular terms. Now, how are the rotational or the angular terms related to the linear ones? So here's a relationship that we already saw from up here. So the arc length is radius times theta, where theta is measured in radians. Then if we take the derivative with respect to time of s, we get the tangential velocity. So tangential velocity is r times omega. The derivative with respect to time of this equation gives us tangential acceleration is r times angular acceleration. And then also remember that we had the radial acceleration, which was the same as the centripetal acceleration, and that's still the tangential velocity squared divided by r. Then if we substitute for v squared, r squared omega squared, and divide by r, we end up with the centripetal acceleration or the radial acceleration being omega squared times r. So now let's look at a concept of rolling motion. And the type of rolling motion we are considering here is pure rolling, where there is no slipping at the point of contact between the object that's rolling and the surface it is rolling on. So we have an example here of pure rotation. So here's my bicycle wheel rotating about its center of mass. So we notice that the center of mass is not going anywhere, it's just staying stationary, and all the points along the bicycle wheel are rotating at a constant rate. So this is basically back to what we did before with uniform circular motion. We have this bicycle wheel rotating in a uniform fashion. There is no tangential acceleration to this bike wheel. Now, we actually don't want the bicycle wheel to just stay here. When a bicycle is rolling, it's moving from here to somewhere else. So there is a translation in addition to that rotation. So if I break up that rolling motion into just pure rotation and pure translation, I notice that all points of the wheel in this pure translation are moving to the right at the same rate. So I have a motion of the top of the wheel, the center of the wheel, and the bottom of the wheel all to the right. So I'm going to draw some arrows here. They'll disappear soon, but here is the tangential velocity of the bicycle wheel, and it's going in the opposite direction here. Whereas in the pure translation, it all moves to the right at the same rate. So we have the same velocities over here. So now, if we put these things together, then we end up with pure rolling that looks something like this. There is my bicycle wheel moving. So let's look at the vectors that I drew earlier. So I have my tangential velocity in this direction there, my tangential velocity in that direction here. And then I'm just going to randomly draw this. I can't just pinpoint them. So here we have the velocities of the top of the wheel, the center of mass, and the bottom of the wheel. So if I claim that rolling motion is a combination of pure rotation and pure translation, then when I add these together, let me bring my wheel back. So when I add these things together, I end up with two velocities at the top, with one velocity at the center of mass and no velocity at the bottom of the wheel. So again, what I did here was add the velocity at the top due to just pure rotation to the velocity at the top due to the pure translation and ended up with two velocities over here. Then I added the velocity at the center of mass here, which is 0, to the velocity at the center of mass over there, and ended up with just this one vector here. And then adding at the bottom a vector that goes to the left that's equal to a vector that goes to the right, those two cancel out, and we end up with no velocity at the bottom of the wheel. So what exactly is going on? Well, in order to have this pure rolling, so there's no slipping, the bottom of the bicycle wheel has to grip the ground and then propel it forward so that this point goes faster, and then the next point is going to move over and grip the ground for a split second, so that the wheel basically does this type of motion, a combination of pure rotation and pure translation. So then the thing that we have to remember is that every time the bicycle wheel touches the ground at a point, that point grips the ground, is 0. It has a velocity of 0 for a split second, and then the inertia from the wheel having a higher velocity up here makes it move on to the next point that will grip the ground and continue this motion. So then velocity at the bottom here is 0. The velocity of the center of mass is v. That's the velocity of the bicycle itself. So if you are riding on the bicycle, this is the velocity you're going to be traveling with. But the top of the wheel will have twice that velocity. So we looked at the rotational variables, and we didn't say anything about vectors, but are they vectors too? I mean, we knew that displacement, velocity, and acceleration were vectors. What about the angular counterparts? The answer is yes. Yes, they are. And the direction is going to be given by the right-hand rule. And let's look at this little video here to illustrate how to do this right-hand rule. So here we have the bicycle wheel rotating counterclockwise like this. We place our right hand in the direction of motion of the wheel, stretch out the thumb so that it points out, and we notice that it points out towards us from the wheel. So let's do that one more time. The hand goes in the direction of the rotation of the wheel, so the fingers are in that direction, and the thumb points out towards us. Now, had the bicycle wheel been going in the opposite direction, then the hand would have come from this direction and the thumb would have been into the bicycle wheel here, into the image. So the direction of the thumb is going to be the direction of the angular velocity. Now, what about angular acceleration? So remember that if you have an object that is accelerating, that means that the direction of the acceleration is in the direction of the velocity. So velocity is increasing, acceleration is in the direction of the velocity, so the direction of the acceleration is the same as the direction of the velocity. Now, if the object is decelerating, which is what happens in the example here with a bicycle wheel, so we start out with a high velocity and then it stops, that means that the bicycle wheel was decelerating, which means that the direction for the acceleration, for the angular acceleration, was in the opposite direction of the direction of the angular velocity. So the angular acceleration for the bicycle wheel was into the bicycle wheel as we're looking at the image here.